Okay, we're going to start into chapter 4 now, and the topic of that section is probability. We're going to talk about basics, and then we're going to talk about some more complicated things further on. And this is that little area between descriptive statistics and inferential statistics that we need to be solid on before we go into inferential statistics, right? So we've talked about already gathering data, organizing data, presenting data, looking at measures of center, looking at measures of variability. There's 4 measures of center that we covered, 4 measures of variability. Hopefully you remember the mean, median, mode, and mid-range for the measures of center. And then variation was range, standard deviation, variance, and then coefficient of variation. Let's take a look at some basics here with probability, and please take your time with this. Spend more time with chapter 4, especially towards the end, because this turns out, believe it or not, to be the hardest section or chapter, actually, I should say, in the entire semester. Probability is pretty tough for people. One thing that I'd like you guys to note, though, is the proverb, the lot is cast into the lap, but its every decision is from the Lord. And that's just to say, be convinced that there is no such thing as a random or coincidence. Even in the algorithms that we create for randomness to happen, there are algorithms, right? So just be convinced as we go through all of these probability exercises that when the actual event happens, it's not just something completely random. Okay, a lot of this is definitions at first, and then we'll get into some exercises. So the first one is, it says here, an event is any collection of results or outcomes of a procedure. And so here's an example of the event: rolling a pair of die and getting a 7 as the result. So when we say rolling a pair of die, usually the result of those two would be added together. And so rolling a pair of die and getting a 7 is an event. A simple event is an outcome or event that cannot be broken down into simpler events. A simple event would be rolling 1 die and getting a 5, right? This previous one is not a simple event because you could have 7 be attained by rolling a 1 and a 6, or right, a 2 and a 5, or 3 and a 4 on one of the pair dice. And then that would be a kind of a compound event when you roll 2 dice. But when you roll 1 die and get a 5, that is called a simple event. The sample space is very important. The sample space for a procedure consists of all possible simple events. So all of the possibilities that could happen, that's something called the sample space. Just think about atmosphere or the cosmos. Space. What are all the possibilities given the constraints that we've described? And so sample space could be rolling a pair of die. And in fact, let's take a look at that. If you roll a pair of die, what are the possibilities here? So on the first die, I can probably make them different colors just so we're getting more used to this. We could say, let's make one of them red. One of the dies would be red. And so I'd have 1, 2, 3, 4, 5, and 6 on a regular 6-sided die. And then we can also have green, right? We can have green, for instance, a green die. And then those numbers would be 1, 2, 3, 4, 5, 6. And so if we were going to do this and say we're going to do the addition of the 2, then I have 1 plus 1 is 2, 2 plus 1 is 3, so I get a red 3 and a green 1. 4, 5, 6, 7, 2, 3, 4, 5, 6, 7, 8. And I'll fill this out. This is the entire sample space of what the possibilities are of a red and a green, 2 pair or 1 pair of die being rolled. Right, 4, 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, 7, 8, 9, 10, 11, 12. So these are the only possibilities. Either you get a 6 and a 6 and so forth. Notice the longest or the highest probability of getting something would be actually a 7. because there's more 7s than any other value. But this would be called a sample space when you roll a pair of die and add the two numbers. Okay, so some more notation. P, capital P, denotes the probability. Usually capital letters A, B, C denotes events. And then P of A, just like function notation from algebra, that denotes the probability that event A occurs. So let A be the event of rolling a 3 on one 6-sided die, right? Find P of A. Well, if we go about that, it says just one die, one 6-sided dice, right? And there's a couple of ways that we can do this. I'm going to go into a little bit in depth, but the possibilities are 1, 2, 3, 4, 5, and 6. And so if I want to find probability of A, where A is the event that a 3 actually comes up, then there is how many 3s? How many 3s divided by how many possible outcomes? Right? That's the total in the denominator. So I'd have 6 outcomes. Of the 6 outcomes, how many are 3s? One of them. So that would be the probability, 1 divided by 6. And we can leave that as a fraction or convert that into a decimal. Right? That's the idea behind probability. I could have 1, 3, 3, 4, 5, 6. Suppose I have a dice that had 2 number 3s. Then the probability of A, where A is the event that a 3 shows up. What's the total number of outcomes? 6. What's the total number of 3s that I have? Would there be 2 3s? And so 2 out of the 6 is a higher probability. Yeah, you can simplify this to 1/3. 2/6 is a greater probability than 1/6. So you can increase the chances that you get a 3 when you roll one 6-sided die. Okay, so that is the denotation for probability. Now let me go into depth a little bit more. There are 2 ways to approach probability. One is the classical approach that we just went through an example of. This requires each simple event to be equally likely to occur. And so the probability is the number of ways that A can occur. So how many 3s did we have in the first one? And the number of different simple events that we have. There was a total of 6 possibilities, or 6 outcomes. And so let A be the event of rolling a 3 on a pair of die. Find probability of A would be an example. Let's do that. We already have this set up. Here's our sample space, right, of a pair of die. And how many different possibilities do we have? Well, we have 36, if we count them 6 times 6, 36 possibilities of getting numbers where on a 6-sided die. And there's only these right here where we can get a 3. So how many total 3s are there? Probability of A would be is the event that you get a 3, let's say. You get 2 3s out of 36, or 1/18th, right? That's the probability of getting a 3 when you roll a pair of die. Again, granted that you're counting the 2 the dies are different, like different colors. Okay, so that would be the classical approach to probability. Number of ways that A can occur, divided by the number of different events that could happen. There is something called a different approach. There's something called relative frequency approach to probability, and that is the probability of A is equal to number of times A has occurred, divided by the number of times the procedure was repeated. So, for example, you can do an experiment, sit near a very dangerous curve in a roadway, in a highway, and then count the number of crashes that can happen. That's the example here. Find out the probability that there will be an accident on a particular freeway, right? So we can make a little table for ourselves and say, okay, number of cars, and then number of accidents. Number of accidents. And so what we could do is do a tally mark, right? We can say, okay, 1 car passed, and we had 0 So no number of accidents. Let's say 2 cars pass and you get one of them to be an accident. Well, the number of accidents then in that case, the probability of being in an accident on that freeway curve would be 1 out of 2, or 50%. That's a dangerous 50. 50% is high. It's a dangerous freeway curve. Let's say if we do continue, 3 cars pass and you get 1 accident. 4 cars pass, 5 cars pass, and you get, let's say, 2 more. So that means 2 more accidents. So 3 out of 5, right? 3 out of 5, and I can do that a little bit more. There we go. That's higher than 50%. But as we progress in counting the number of cars that keep going, getting through, you would actually be approaching to the theoretical probability, the actual probability of being in an accident. So, and that is something important, actually. The law of large numbers is something that we glean from this process. Okay, so that's the other approach to probability. It's not knowing the total number of outcomes, but you want to know what the probability is, so you count the total number of observations that you have, number of cars that pass on a freeway curve, and then the event that you're interested in is the number of cars that are in an accident. So you take the number of accidents and divide it by the total number of cars that went by to get the probability, okay? So that's the second approach, the relative frequency approach. You count actually the frequency of the events. And as I mentioned, the law of large numbers is the result or the next step to think about. As a procedure is repeated again and again, the probability of an event tends to approach the actual probability. As a procedure, other way of thinking about this is that as a procedure is repeated over and over, the relative frequency probability of an event tends to approach the actual probability, right? If I kept sitting there on the freeway curve and watching 1,000, 2,000, 3,000, a million cars go by, the actual probability of getting into an accident, I would be approaching for closer and closer, right? So, oh, by the way, this is a reason to quit while you're ahead when gambling, right? Because there's a small probability of winning when you're ahead. Note that eventually your probability of winning actually will come down, so to the actual probability. Therefore, if you're ahead in a game, just run out of there and say I won, and that's it. One important thing, though, before we continue, a common mistake is to assume each outcome is equally likely when we know nothing about the likelihood of each outcome, right? So, for instance, if we were going to take a look at this car issue, I would be assuming that all of the cars, the probability of getting in an accident on a certain freeway curve, each car is equally likely to overturn, for instance, right? If it's a dangerous freeway curve. But we know that the taller the car is, the more chance it has to actually overturn, right? If it's a dangerous S-curve, for instance. So don't assume things that you're not sure about. Maybe they are all equal, maybe they're not all equal. So be careful about that when you're actually doing probability. Probability has limits. Probability of an impossible event is 0, like finding a square circle, right? Or being 2 places at once. The good Lord decided we're going to actually get from one place to the other, and it's going to take some time. Probability of an event that is certain to occur is equal to 1. And so I'll ask this on the test. I'll give you guys questions, and I can give you limits, for instance, for probability. And your job is to remember, and here's something that people forget, that this is not just less than, this is less than or equal to. So the 0 can be attained. There are impossible events, right? And there are certain events, or events that are certain to occur. So less than or equal to. And the probability of A is between 1 and 0, right? 100% if it's certain, and then 0 if it's impossible. Here's another way of looking at it. We have certain, which has a probability of 1. There's a 50-50 chance at 0.5, and then 0 is an impossible event. Okay? A couple of examples. Winning the lottery, 0.00, that's really, really small. So be very careful. And I know that we have a lot of hope in our hearts and desires to get rich, but be very careful. Winning the lottery is really, really unlikely. Um, and then being struck by lightning is also unlikely. It might be more likely in California with all these fires that we've had, but and will have maybe, I don't know. Typically, any probability less than 0.05, please note 0.05, is considered unlikely. And we're actually going to connect that with a bell-shaped curve a little bit later, right? 0.05 is considered unlikely. Okay, so these are unlikely things because they're less. The probability is less than 0.05. So let's practice right now. I'd like you guys to pause the video and answer these questions. It says, roll a six-sided die and observe a 4. Find the probability. And there's some vocab practice. So pause the video and see if you can answer these questions. Okay, what is the experiment? The experiment is rolling a die. What is the event? Well, we want to observe a 4. What's the total sample space? On a six-sided die, there's 6 options. The number of outcomes favorable to A is 1, right? Because we're interested in observing a 4, and there's only one 4 on a six-sided die. Number of total outcomes is 6, right? And then what is the probability? Probability of getting a 4 out of the 6 possibilities is 1/6. So 0.167, or about 16 or 17% chance. We're going to do some exercises with cards. If you haven't been exposed to a deck, like I at one time didn't know how many of each card there were. There's 4 suits. We have 10, A through Ace through 10 would be the numbers, and then we have some face cards. And let's agree just for our class that the face cards are just going to be the Jack, Queen, King. Okay, so there's 3 face cards in each suit, or a total of 12 face cards. So let's answer some questions. What is the probability of randomly choosing a diamond from a standard deck of cards? Well, the probability of X equals getting a diamond would be there's a total of 52 cards, and then 13 of them, 1/4 of them, are diamonds. So what's the probability? It's 1/4, or 0.25. Okay. Tossing a coin 3 times and observe exactly 2 heads. This is a slightly different exercise. So you want to toss a coin 3 times and observe 2 heads. What's the experiment? What's the event? And what's the sample space? Please know that there are 3 outcomes favorable to the event and 8 total outcomes, right? So if you toss a coin 3 times, that's the experiment. You observe exactly 2 heads, that's the event that you're interested in. And so what's the sample space? Well, if you flip a coin once, you can get heads or tails. You flip a coin again, you get heads or tails. And then flip a coin 3rd time, you get heads or tails. And there's a whole bunch of combinations of those. So, and that's the sample space right in front of us, right here on the slide. Heads, 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 tails, heads, tails, heads, and so forth, right? Now, since I know that each one of these are independent, let me go to my scratch paper and show you guys that I could actually do something called a probability tree, a tree diagram. So, for instance, the first toss would be heads or tails, right? Heads or tails. The next toss would be either heads or tails. And the 3rd toss could be heads or tails. Heads, tails, heads, tails, heads, tails, heads, tails. So this is the first toss, then this is the 2nd, and there's the 3rd. Okay? And there's a total of 8 possibilities. A total of 8 possibilities. How many of them have, let's see, how many heads were we interested? We wanted exactly 2 heads, right? So we don't want more than 2 heads or less than 2 heads. We want exactly 2 heads. How many of those have exactly 2 heads? There's 1, there's 2, and there's 3. So 3 out of the total 8, or 3/8, or 0.375. There's about 37 or 38% chance of getting exactly 2 heads when you toss a coin 3 times. Okay, so we created a sample space. We honed in on a particular event, and the sample space items went in the denominator, and the event we're interested in, that was the numerator, or the possibilities of getting heads, 2 heads exactly, is in the numerator. There's also something called complementary events. A complement of event A is denoted by A bar, or sometimes a superscript C, and it consists of all outcomes in which event A does not occur. So we have probability of A and the probability of not A. That's how we read it, not A. If we roll a pair of die and A is the event that we roll a 5, determine what the complement is, right? And you can write this a couple of ways. Here, let me go back to here's a pair of die, right? If I roll a pair of die, then I have a whole bunch of possibilities. Now, if I also take a look at the number 5, right? That was for my, number 5. So here I'm going to circle, it looks like I have 4 5s, right? So 4 out of 36 is the probability that I get a 5. Probability that we have not a 5, I know we were asked just to find the event. Well, that would be the rest of it. 36 minus 4, which would be 32. 32 out of 36. That's the probability of not getting a 5, because not getting a 5 means you got all of these numbers, right? All of them except the 5. So that's how we answered that question. That's the complement, not 5. And there's a property that complementary events have, namely that you can go between one and the other by just doing one minus the other. So example is, if the probability of something occurring is 1/6, what's the probability that it won't occur? Well, it's the rest of it, 1 minus 1/6, or 5/6. That's the probability that it won't occur. Let's practice that a little bit. Here's a study of randomly selected American airline flights showed that 344 arrived on time and 56 arrived late. What's the probability of flight arriving on time? What's the probability of it arriving late? Let's let A be equal to the late flight, and a complement then would be the on-time flight. Notice that you don't have any gray area. It's one or the other, right? So either you're late or you're on time. And so if we're going to take a look at the complement, probability of them being on time would be 344 divided by the sum of 344 plus 56, right? And that ended up being 0.86, or 86%. The complement of that would be 1 minus 0.86, or 0.14, right? And so what is the probability of a flight arriving on time? On-time flight would be 0.86, high probability, right? And late would be 14% chance. So that's how we counted the probabilities by using complements. Please note for yourself if something is a complement. You might be able to use that to your advantage on finding the probability. Round-off rules for probabilities. Give the exact fraction or decimal, or you can round off the final results to 3 significant digits. So 1/3 is exactly exact and could be left as a fraction, or you can round it to 0.333. 0.0003875 would be rounded to 0.00388, right? So 3 significant digits. And so in the next section, what we're going to take a look at are some rules, the addition, and in the section after that, we're going to talk about multiplication. And again, my approach to this is to show you guys the formulas, and there are calculator functions for this, but show you the formulas and how to work them out, the formulas, increase your ability to count the probability using just logical thinking, logical approach, and formulas. So we're going to try to do both here, use the calculator and not use the calculator, so that we gain intuition and just have a solid understanding of this. So what I'd like you guys to do right now is to go and try as much homework as you can for section 4.2.